Hey folks, now we're going to look at using the law of sines in the opposite direction, finding angles instead of sides. Before we do that, let's solve this triangle, and we will be off. Okay, I said before we do that, but clearly that's a lie because this first problem, if you look at the opposites we have 63 degrees opposite of that 5.5 side. And then the other piece of information we have is this 4.7 side, which will tell us what angle B is. So, what are we trying to find? This time we're trying to find an angle. So I'm going to set my proportion up as the sine of angle B divided by its opposite side, 4.7, equals the sine of the angle I know, 63 degrees, divided by its opposite side, 5.5. And I can rearrange this as the sine of angle B equals 4.7 times the sine of 63 divided by 5.5. And if you do 4.7 times the sine of 63 and divide it by 5.5 in your calculator and get a decimal as an answer, you will be like, wait, why is that angle so small? Well, you're forgetting that that is the sine of B. That is not B itself. It is the sine of B. And so, what we now need to do is take the inverse sine of both sides. On the left, that will give us B, and on the right, we'll have the sine inverse of that whole mess, 4.7 times the sine of 63 divided by 5.5. And on your calculator, I would type it like this. I would hit second sine to get your sine inverse. It'll give you a parenthesis like that. I would type 4.7. I would hit the sine button. It gives you a parenthesis. Types your 63. You have to then close that parenthesis and then divide by 5.5. Enter it in exactly like that, and you will be happy. You should find that B is 49.588 degrees. And once we have B, since we also know angle C, we can find A by subtracting those two from 180. So 180 minus 49.588 minus 63 equals a number. And in this case, that number is 67.412. But we are not done. We still need to find side A right there. And so let's set up a proportion now that we know angle A. We can say that A divided by the sine of 67.412 equals, we want a ratio we know. Let's just go with 5.5 divided by the sine of 63. Then we can rearrange that to get A equals 5.5 times the sine of 67.412 divided by the sine of 63, and crunch it in your calculator. You should find that A is 5.699, so we found all the sides and all the angles of that triangle, which means we have solved it. Are you getting dizzy? Yeah, probably. My bad. But we are now in the realm of the problematic law of sines cases, where you have an angle and then two adjacent sides. When you have that situation, you run into some problems, and so we're going to run through a little exercise to see what could happen. First off, we want to know what is the minimum possible length of side A that makes this a triangle. Remember that side A will be opposite of angle A, so we're talking about this side over here, and if that's A, we want to know what is the shortest possible length it could be to create a triangle. Well, Euclid being the father of geometry, said the shortest distance between between 2 points is a straight line, and that means the shortest distance from vertex B up there down to this base, AC, is actually going to be a perpendicular line. Imagine if it wasn't. Imagine it went out slightly, like say that. Well, then, if you look at that pink and blue line as creating a little right triangle, the blue line is the hypotenuse, and so it would have to be greater than that pink side C. Same thing if we went in that way, and so pretty straightforward to see that that perpendicular line right there has to be the shortest distance between B and C, which means it has to be the smallest value of A for which this triangle could even exist. Now again, make note of what the conditions are. We're saying we have a fixed angle of 33 degrees, we have that fixed side length of 15, and we're looking at possibilities for side A. And so how do we find side A if this is a right angle? Well, if it's a right angle, it's a right triangle, which means we can use trig. And so we can say the sine of 33 equals the opposite side, which is A, divided by the hypotenuse, which is 15. And so 15 times the sine of 33 equals A. And we find A to equal 8.17. So 8.17 is the minimum possible length of side A that guarantees this is a triangle. But imagine if A was less than 8.17. Imagine if A was just that length right there. Well, then there is absolutely no hope of side A reaching that base AC. And so if A was less than 8.17, if A was less than 8.17, there would not be any triangles that exist. This would be exactly one right triangle, but if A is any less than that value, no triangles could possibly exist. And so that is one possible condition when you have this angle side-side case. So if A is an acute angle right there, and A is less than the value of that perpendicular distance, then we know no triangles will exist. If A equals that perpendicular distance, then we have exactly one right triangle. So those are two cases out of four. Let's look at the next one. Imagine if A equaled 20. Well, A is going to be equaling 20, coming out like that. We want to find the measure of angles B and angle C. Okay, well, if we do that, then we could set up a proportion. We could say that the sine of angle B divided by lies, I couldn't do that because I don't have opposites there. But I could say the sine of angle C divided by 15, the opposite side, equals the sine of 33 divided by 20. And so then, that means the inverse sine of 15 sine 33 divided by 20 will equal C. Let's crunch that. You should find that angle C equals 24.109. If you didn't get that, make sure you enter this into your calculator correctly. I would type second sine to get the sine inverse button like that, and then I would go 15 sine, gives you the parenthesis, 33, close the parenthesis just once, divide it by 20. That will get you your correct answer written just like that. If you add extra parentheses, if you put a parenthesis there, that's going to close off the sine inverse function only around the 15 sine 33. And we need it around that 20 as well. If you want to put one there, you can, but you don't need it. You should get 24.109, which then means to find B, we could take 180 and subtract what we know, 33 and 24.109 to get 122.891. So, let's label this real quick. 24 point, what was it? 109. 109. And there we get this big old obtuse triangle. Now think about the conditions here. A was 20. What's significant about that 20? Well, the significance is that it was greater than that known side length of 15. When that happens, we will get exactly one obtuse triangle. And why am I saying exactly one? That's kind of weird. Well, imagine that this side right here would pivot, because remember that angle B is not fixed. Imagine if I were to drag that side that way. Could I line it up again so that this bottom point right there landed on side AC? Well, imagine if I moved it this far. C would be like down there, so that wouldn't work. Imagine if I went a little bit farther and got there, it'd be like that. If I wanted that point, C, to lie on that bottom line right there, I would only be able to do that if it went all the way over there, given that side length of 20. But now the problem is I'm no longer using that 30-degree angle, 33-degree angle, which means I can only have that one obtuse triangle. I know that was a weird explanation, but I think it'll make more sense in a moment. But the important piece is we know that if A is greater than or equal to that given side length of 15, we will get exactly one obtuse triangle. Think about if it were equal to it, it would be directly on that line, so that would not be a triangle. So again, we only get that one case by swinging that side out to the right. So if A is an acute angle, and side A is greater than or equal to that known side right there, we will get exactly one obtuse triangle. But what about this case? What if we have this situation right here, if A is 10? Well, to help you visualize this situation, I'm going to draw something in. I am going to draw this line out. That was bad. I'm going to do it again. I'm going to draw that out right there. Still bad. Let's go one more. No, that's bad. That's good enough. I'm going to do this. I'm going to say that A is 10. But actually, what I'm going to do right now is I'm going to make this a right triangle. I can't talk today. I'm going to call that point D, and I'm going to make this an isosceles triangle, since I can talk again. Notice it's an isosceles triangle because we have two legs that are the same length, 15 and 15. Isosceles triangles have congruent base angles, so that's also 33 degrees right there. So we have triangle ABD is isosceles. Okay, well, why am I doing this? Why is this important? What happened to A? Well, now I'm going to draw A in with a red line. We know A is 10, so if A is 10, it's going to be a little less than 15, means it's going to come down something like that. And let's call that 10 right there, and that is side A. So now for the time being, let's focus on this pink triangle ABC right there. Okay? So we have this case, boom, 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 10. We don't know angle B, we know angle A is 33, 15, and C down there. And let's solve this triangle. What do we know? Well, we have two sides and an angle, so we can find angle C now. So angle C is going to equal the inverse sine of 15 times the sine of 33 divided by 10. Check me, make sure I set that up correctly. We should find C to be 54.781 degrees. And if we have C, we can find B by subtracting 180 minus 54.781 minus 33 equals 92.219. And so now we just need to find that third side, AC. And so to do that, third side is B. We're going to say B equals, what is B going to equal? B is going to equal 10 times the sine of 92.219 divided by the sine of 33. And again, check me, make sure I set that up correctly. Using the law of sines, you should be able to do that. find 18.347 for that side. So now we have completely solved this triangle using the law of sines. No big deal. It's kind of a big deal. It's pretty awesome. But we have that triangle, and everything we've done, totally valid. But we have a little bit of a problem. What's the problem, you ask? Well, look at this purple. That doesn't show up well. Look at this green triangle here. We have the same starting conditions. We have a fixed angle of 33 degrees, just like that right there. We then have a side length of 15 attached directly to it. And then we have a side opposite of the 30-degree angle of length 10. But that green triangle is clearly not the same as that pink triangle. Clearly totally different triangles. What's going on there? Same starting conditions, different possible triangle. Well, let's solve this green triangle and see what happens. We've got that 33, we've got the 15, we've got the 10, and that's all we know. What can we do? Well, let's see if we can use the law of sines. Law of sines says you can find a fourth piece of information opposite of something you know. That means we'd be finding that angle right there. But that is a super big problem, because if we set this proportion up, we would say that the sine of angle C over 15 equals the sine of 33 over 10. And that's the exact same thing we did to get this 54.781 degree angle. And so clearly, when we do that, we're not going to get the correct value, because that 54.781 degree angle and this green angle right here cannot be the same value. Notice the relationship between those two. They're on a straight line. They form a straight angle. That means they're supplementary, meaning they add to 180 degrees. So if we want that green angle right there, we need to take 180. We need to subtract the angle that we already found, 54.781. Doing so, you get 125.219, an obtuse angle. And we can use that to find the third angle in the triangle, doing the same thing. This time 180 minus what we just found, 125.219, minus the other angle we know, 33. We get 21.781. And so we can fill out this triangle a little bit. And so now to solve this triangle, we need to again solve for side B. So we're going to set up a little proportion here to do that. We are going to say that B over the sine of 21.781, that equals, what do we know, equals 10 over the sine of 33. So then B is going to equal 10 times the sine, 21.781, divided by the sine of 33. Plug that into your calculator to get this number. Doing that, you should get 6.813. And so we've now solved this second triangle as well. But this is a super big problem, because with the same initial conditions, 33-degree angle, adjacent or connected side of 15, and then an opposite side of 10, we end up with two totally distinct but totally valid triangles that give these conditions. And again, they're both just part of that big old isosceles triangle there. So if you think about it, anywhere that I draw a line in between those two sides is going to give me this situation where I have two possible triangles. And, well, what then are the values of A where this happens? Well, if A is going to be bigger than 15, then it wouldn't happen, because we'd only end up with like one big old obtuse triangle out like that. We looked at that a moment ago. Or if it's equal to it. It can't be equal to that right angle value, because then we just get that right angle But anything between those two pieces will give us this weird two triangle situation. So if A was greater than that value we found for the right angle, 8 point, was it 71? No, it was 17. If A is greater than 8.17, but less than that given side length of 15, we will always end up with this weird two triangle case. That's a problem. But why is that even happening? Well, think about what we ended up with. We ended up with an expression, sine of c equals 15 times the sine of 33 divided by 10, and that fraction right there, that ratio, has a value. It's that decimal, 0.817. And you need to think about the inverse sine function and how it works. The inverse sine function is defined in these two quadrants, which means the output of the inverse sine function will only give you a value between negative 90 degrees and positive 90 degrees. But for us, when we're dealing with these triangles, that means we're only ever going to get an angle between 0 and 90. We'll only ever get that acute angle. So when we did the inverse sine of that value up there, we got this value right here, which gave us an angle of 54 point something degrees. But the problem is, if you think about sine on the unit circle, sine is a y value. This angle right here also gives us that same sine value of 0.817. But the inverse sine function will never ever tell us that whole obtuse angle right there, because it can only ever give us that acute angle, 54.7 degrees. So you have to be very, very careful, because sometimes, given this situation where you have an angle and then a side, the donkey case, you might be looking for this obtuse angle, but you'll never find it. And you have to use the context of the problem to determine, should it be the acute angle or should it be the obtuse angle? If it's the obtuse one, then you need to take 180 and subtract whatever your calculator tells you for that acute angle. That's a problem, but we will look in the next video of how we can address this problem. But to summarize, if the value of A is between that right angle value and the length that's been given to you, you will end up with two possible distinct triangles. So let's run through this real quick. Let's do one problem all the way through. We want to know, what are the conditions on A to give us these different cases? Well, the only operation we need to do is figure out that value right there, which is just 9 times the sine of 17. Which is 2.631. And so, if we want no triangles to exist, we need A to be less than 2.631. If we want one right triangle to exist, A has to equal 2.631. If we want one obtuse triangle to exist, A has to be greater than or equal to the given side length, in this case 9. And if we want two triangles to exist, we need A to be greater than that right angle distance, 2.631, but less than that side given of 9. Those are the four situations right there. This will totally be something I ask you on your test.